Thanks so much, everyone, for sticking around till the next to last talk on this Easter. Is anyone a little bit tired? Okay, so I'm going to stretch a little. Join me if you want. Help me calm down. It'll help you maybe stay awake. And I hope that I can keep you awake with what I have to say. I want to thank the organizers, of course. This is so cool to be here at the first conference of Clojure North. I'm coming from Cleveland, and I'll tell you more about my story as we go, but I want to feel like I'm North enough to be a little bit of part of this community, so it's quite an honor to be invited here. I've written Clojure for a number of years now, but this is the first time I've actually gotten to come to a Clojure-specific conference, so it's really great to see people who are like all on the same page. So I'm coming from AppsFlyer, and what do we do first? Mobile attribution and measurement and analytics, and I'll explain this a little bit more quickly. And actually now, not just mobile, we're now moving into a web mobile cross-device type of attribution. And that's going to be more and more important in the future. But what's shown here is kind of the typical vanilla flow. So the problem we're trying to solve is someone is using a cell phone and they click on an advertisement and they install an app. We offer a service to the app owner that tells them who was sending that advertising. Was it Facebook or Google? Which campaign? That's the way they can optimize their advertising budget much more effectively. So from the cell phone, there might be an ad click, and the way we do the flow is we get the click first in our server so that we can record that we saw it, and then we redirect the client straight to whichever app store or Play Store they need to go to. Then they install the app, and then eventually they're going to launch the app. This could be 5 minutes later, it could be a day later. And then we're going to get the launch event from an SDK embedded in that app by the app developer, our SDK. And then based on that launch, we're going to be able to attribute the install back to whatever the original media source and campaign that was driving that traffic. And then for the life of that install, we're going to continue to get events from the cell phone, from the SDK, whenever the user makes a purchase, whenever they open the app. And this allows the client to learn what the lifetime value of that install is. And so we've been growing pretty remarkably. It's been quite a ride here. So here over roughly the last 2 years, we've gone from 7 billion to 40 billion events a day, and it's not stopping there. Currently, we're hitting like 70 billion events a day from these SDKs that are embedded in the apps. And so dealing with this incredible traffic, and not just the traffic, but the growth of the traffic has been quite a ride, and that's what I want to tell you about in this talk. Because of course, once you get a solution, we're always thinking, well, is this solution going to work for 2x? Is it going to work for 5x? Is it going to work for 10x? And we're really trying to design for the 10x edge of the traffic. So now that I've kind of given you an overview, we're going to dive in more to the architecture, and really I'd like to get interrupted with questions if anyone has them. I know it's getting a little late, so if it's a little more interactive, that's totally fine with me. So also, I got a bottle of wine as a gift from the organizers, but I'm not going to be able to take it back with me. So first question, you can have a bottle of wine too. So if that'll, it's not, that question won't count, but it's a Georgian wine, which is kind of interesting. I'd never had, so. So initially, like a lot of startups, this was a 2 or 3 person developer team, and the stack they picked was a great stack for where they were at, which was Python for all the coding, both basically the backend and the web-facing, client-facing part of the app. Redis for PubSub, MongoDB for the main data storage, and CouchDB for a document store, mainly for the permissions and the domain model. So like, who are our clients, what permissions do they have, which apps do they own, stuff like that. And this worked pretty well, but if you know anything about these technologies, you'll probably know that they worked pretty well until they didn't. And so, for instance, Python is a really nice language. It was probably the perfect choice at this time. The thing they needed to get done was to get a product out there, get traction with a client base, prove themselves that they knew what they were doing and had something that was going to fit the market, and it worked perfectly for that. But once they started seeing traffic in the millions or hundreds of millions of events a day, you know, we're still talking like a fraction of a percentage of what we're seeing today, but even at that level, these technologies were really hitting their limit. And so then, over time, these were slowly replaced by other technologies, and I think, you know, for this conference, up top here we have Clojure, which was the choice of programming language to replace Python. And here there were other choices, right? And so they spent a month or so going through the other choices, and some of the other things on the table were, you can probably guess, were Scala. They also considered taking the Python and then rewriting some of it down at the level of C code where it would be more performant. Also, they considered ML running on the CLR. And there are a number of reasons for each of those not being the best fit, but I think really for this talk, what I want to emphasize is that the choice of primary language here, it really affected the evolution of the whole system at a much deeper and more philosophical level, because the opinionated choices in Clojure really permeated the whole system and the whole way of thinking about programming and the design of the system that they created. And so by buying into Clojure as a language, it wasn't just a performance boost from Python. It was a change in the way of thinking, and bringing those changes in thinking up and down the stack really had benefits everywhere. So if you haven't seen this talk, it's an old one, but a good one. When I joined the company, this was on the required training list. Go watch this talk. And it took me a few times to really get it. But what Rich Hickey is talking about is what can we learn from programming languages and bring it up to the systems level, and what can we learn at the systems level, and bringing back down into programming languages. And as we go through the rest of the talk, I'll point out a couple of the points from this talk that were really important for us. And I just want to step back and bring in a little my background. So around this time, I was working as a postdoc in biophysics, and I was working in Israel, where I had gone to do a postdoc. And around this time, as they had just picked Clojure and were starting to develop out the stack, I had also run into these videos online by Rich Hickey that seemed to really resonate with me, and I'd always written a lot of code for my own personal data processing, and Rich Hickey was talking about how there's this kind of inevitable march towards a ball of mud and a hairball, and I could feel that even in my own personal projects. And so when he was talking about how there's ways out of this problem, it really resonated with me, and I went and I learned Clojure just on my own, and got just totally clicked with me. And around this time, I was at a Clojure meetup, and the AppsFlyer team came and presented their work and said they were hiring. So I went up there and met them, and it worked out, and I've been there ever since. This was about 5.5 years ago. It's been a great time. And since then, like I said, I mostly work down in the data team. I think given my background in science, it's a good fit. So if you have more data-related questions, feel free to reach out to me. But most of this talk will be about kind of the full stack at our team. So kind of as we went along, some of these other technologies also fell by the wayside. I'm going to talk a little about the Toku Database. We make really heavy use of key value stores, distributed key value stores, and as a production system, Couchbase wasn't working well for us, and we've since switched over to Aerospike, which is working super well. And then I'll talk about a lot of these others as we go. Any questions so far, or comments, or cool? So now, kind of almost exactly the same talk, really, I could see yesterday from Alex Hudek from Kira, going through a lot of the same issues that we've gone through as a Clojure shop. Currently, we're hitting like 150-ish developers. I lose track because we're growing so quickly. And running Clojure at that scale is a little hard. And so some of our services now are transitioning into Golang, especially some of the more, I would say, infrastructure type things. There's a pretty successful proxy, which was written in Go, and there the language is a really good fit for a proxy. But for the bread and butter, like taking complicated data, doing a bunch of transformations on it, and putting it back out, Clojure is still our go-to and the best thing we have going. Overall, when we choose things, if we have a choice, we really like to have things that are masterless, that are clustered, and they're redundant, obviously. And here's some examples. So Kafka, we use super heavily, and Aerospike, I mentioned, has been super reliable for us. And recently we switched to using ClickHouse, which also takes the same architectural approach of being a masterless, or at least what kind of has local master and slave setup. Cool. So I've kind of talked in general about our stack, but now I want to show you more specifically, like, how does it work? So there's all these cell phones out there, and they're sending us their events over HTTP, and those all are met by a big bank of web servers. And the job here of these web servers is to do a little minimal transformation, maybe validation on the message, and then just put it into Kafka. Then from inside Kafka, kind of hidden here in this red square are several topics, and the messages will go from one topic to the next through a cascade of small either microservices or mini services, but the point is that not everything happens in one place. So the flow I started off the talk with, where we're matching a click with an install. That matching happens here in the attribution engine. This is an interesting flow. So after the app launches, then often the app wants to know which advertisement got me here, right? So if you clicked on an ad for a vacation in Hawaii, you don't want to open up at the home page or on a vacation to somewhere else. You want to open up in the thing that you started going for. And you don't really care that you had to go to the Play Store and install the app and bring it up. You know, as a user, you don't care about all that stuff. So this endpoint allows the app itself to query our system and find out where the install came from. And then the Kafka queue is eventually persisted out to S3 in a few phases, but one phase is just basically a straight dump of the queue out to S3 into Hadoop sequence files, which is just a flat format that's convenient for us. And so this you can think of as just kind of an extension of the Kafka retention. So normally Kafka would cut your data off at whatever the retention is, but now we essentially have infinite retention because we're dumping it out to S3. Then from there, we typically transfer those flat files into columnar formatted Parquet files because those are super efficient to read and write, and that's what we do all of our batch analysis on down here. But meanwhile, we also are serving a real-time view of the data to our clients, and so another Kafka consumer is reading the relevant data from topics in Kafka and loading it straight into a ClickHouse. And I'll have a little more to say about that later. And then these two are basically kind of the output flow of our system. There's many integrated partners in the ecosystem that want to know what decisions we made. So when we are able to match an install with an advertisement, and if it was the advertisement for a particular ad agency, they want to get a message for that. And so that's what's going on down here, is every time we match a particular ad for this agency, we'll send it to them. And as you might imagine, this system has a lot of kind of fine-grained control over what we send to each partner. Some people want this, some people want that. They want it formatted in different ways. So what are kind of the main things that we've done here? So this is definitely an event-driven architecture, right? We're putting events on the wire and moving them between decoupled services. And if you go back to that talk from Rich Hickey, this is exactly what he suggests. He says, you know, we don't want our microservices system to be a bunch of people doing synchronous calls to each other. We want it to look like a factory where stuff goes in one end, there's a clear progression of transformation, and raw materials come in, and a fully formed product goes out the other end. And this is exactly what we're doing. And the whole time, we're just in a functional programming sense. Each of these microservices takes in a message from Kafka, transforms it just like a function in Clojure would. Maybe it's doing a little bit of mutation of a key value store, but it's still trying to do a transformation, and then it puts it back out. And this functional thinking really helped pervade the whole system. And that was a huge win for using Clojure. I think that's the biggest thing that we've gotten. So we have messages on the wire, and what do we put on the wire? So originally, back in the first iteration, it was Python Pickled messages, which is a kind of a bespoke serialization format that Python gives you. So that's great if you're a Python service trying to read the data, but if you're not, it's not great. So when we started to migrate services over to Clojure, this was a huge problem. Eventually, the solution they came up with was to ease the migration. Clojure services would, I'll jump ahead, Clojure services would write JSON on the wire, and then there would be a shim that would translate the JSON into Pickle so that the legacy services could read it until we had time to refactor those into Clojure and slowly kill them off one by one. So based on the difficulty of dealing with this Python Pickle, I think it largely informed their choice to go with a pretty agnostic serialization of JSON, even though there's certainly caveats with JSON. It's pretty language agnostic at this point, and that was one of the major reasons for using it rather than, say, Eden or something else. But JSON has some problems, and so in certain places, and we're probably going to move to protobuf messages in certain places. In the next few slides, though, I'm going to talk about the trade-offs there that make this choice for us a little bit tricky. So this is, if you squint at our architecture, this is roughly what it looks like, right? We have data coming in from, let's say, the outside world. It goes through services. These are Kafka queues, and eventually, after an arbitrary number of services, we transform the data into Parquet as S3 files. So currently, we use JSON as the serialization format between these, and that's largely great for a couple of reasons. So if this service wants to add a new key, it's no problem. They add it. And then this service doesn't really need to know about it. It's an open format. And then eventually, it'll make it down to the bottom. So that way, recognizing that different teams are responsible for each of these services. One team up at the top of the stack can add some new keys that they need to debug a problem that they're having, and it doesn't affect everybody else. Those keys just flow through silently. But the problem we have is that when you convert the data to Parquet files, you need to have a list of columns. Because it's a columnar format, it's going to take your data and put it into columns. So it needs to know exactly which columns to persist. So here, at this step, we need a rigid schema. So we have this tension in our system that it's great to have this open schema where the keys are flowing through, and you look at what you want, and other keys that other teams are adding, they can just go by you. But then once we hit this Parquet part, it's a difficult step for us because I get a message down here in the data team, and it doesn't come with a schema. I don't know what's in it. And I have to decide which columns to actually persist. So this lower part would be fixed if we switch to using proto-buffed messages, because they have a schema. They tell you which columns are in the message, but the hard part there is if service number 1 wants to add a column, they need the buy-in of everybody in between. Everybody has to upgrade their schema definitions so that it can make it down to the bottom of the stack. And so this is an issue we still haven't solved, and we're not really sure where to go with it. Basically, right now it's really between the JSON and Parquet, I think mainly for performance reasons. The JSON deserialization is surprisingly fast. Something that wasn't obvious to me initially is that JSON looks really huge, but when you compress it, if you have the same keys in every record, they compress extremely efficiently, right? Because compression is based on seeing the same token over and over. So if you have the same key in every map, then it basically gets compressed to a very few number of bits. And so the JSON compression, if you've got largely static schemas, is really good. So in terms of performance, JSON is actually quite good in our system. But what we're missing is some kind of, not type safety, but some kind of schema. And once we get down here to the data team, it can be really frustrating when we get a message and someone upstream has deleted or moved a key by accident, and then we're in trouble, and sometimes we don't realize until we start doing the batch processing the next day that we're really missing something. So these are issues that are tough for us to deal with. So if anyone has thoughts on this, yeah.
How do you deal with backward and forward compatible schemas? And do you have schemas like just before you send that out to Kafka?
Yeah, so in this upper part, in Kafka, we have typically no schema. The service gets a JSON, converts it to a Clojure map, adds keys, removes keys, does whatever it wants, and puts it back on the wire for the next service. So that's both nice because we can move quickly, but bad because we can break things really easily. Once we get down here to the Parquet level, when we convert to Parquet, we need to have a list of fields to convert. And for that, we have a kind of a janky thing that lists all the fields, and it's got versioning by date. So for each date, these are the fields that are going to get converted to Parquet, and then tomorrow they might be a different set of fields that get converted. And that's the best we're doing right now. But along those lines, you know, it makes every once in a while someone who doesn't quite understand how difficult the versioning and the forward and backward compatibility is down here, they'll want to rename a field up top. They'll say, oh, I wrote this service, it was a, you know, a proof of concept, and now I want to rename all these fields. And you're like, oh, no, don't, please. It's just a nightmare. If you rename something, then everything is messed up. And they, you know, they say, oh, I don't like this name. Well, down here, we still have code that reads the old data and the new data, so the field didn't disappear from the code. Now we just have essentially we have an if statement that says, you know, before this date, look at the field that nobody wants to read. And then after this date, so it doesn't even get the field out of the code. It's you know, it's really tough. Yeah. 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 So I'd like to, I'd say in general, like a lot of things, it's really it's an organizational and a people issue, and the pain of not having a schema is felt by the wrong people. So the team that feels the pain is not the team that can actually do anything about it. And so we would need some buy-in at least to be able to force them to use whatever schema system, and to get even that buy-in is hard because they don't feel they don't feel the pain. Yeah. 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 In a few places I've done things like, as the consumer, I've written a separate library just to hold Clojure spec, telling the upstream what I'm willing to accept. And that way they can take the same Clojure spec and validate that their messages are going to be accepted by my library. But that's just kind of it's not like a super global solution.
Have you run into any issues with constantly accumulating on the wire, so to speak? Like as the message gets further and further down that queue, it's always getting bigger, presumably?
Yeah, yeah. That's another problem because, so if you're not allowed to make any breaking changes, the easiest thing to do is just make copies of stuff, or even take whole subtrees of the JSON and copy them to a new place where you can make changes. So you end up with lots of these kind of duplicated subtrees throughout the message, and as a new developer coming in, it's often hard to know which one is the real place to go to find out field X. And it might only be, you might only need to look in the correct subtree in 1% of the messages because there's some product that is the only only product that actually needs this specific version. But it can be really, really hard to find the right field to look at because of this kind of duplication that gets built up. So, to some extent, we kind of have taken, I think you were asking if we could just take away the schema or make it force the schema. So to some extent, the list of fields here that we persist to Parquet is sort of a de facto schema. It says, whatever's going on upstream, once it hits us, this is the list of fields that we're going to carry on with. And so if your field is not in the list, it's it's left out. So to some extent, that already happens. It just happens in a difficult way that can sometimes create friction. So I think you can definitely appreciate we're running a microservices architecture, and the great thing about that is now we've got like 150 developers. We can have small teams of 5, 10, 15 developers that have ownership of a single service, and they can run really fast with it, and that's been really good. But things that have been hard are, coordinating changes between teams. And also, one of my colleagues has made a really good case for and I think the boat has probably sailed at AppsFlyer, but he's made a really good case for having a mono repo with multiple sub-modules, where each sub-module is a service. And that way, every team is both able to inspect all the code, and then if there are things that need to be between services, they can also exist in the repo, and then you can see if you're breaking changes across different teams. So I think if I were making the choice again, I would probably go with that architecture. Although even now, I'm not sure how mature the Clojure like mono repo with multiple sub-repo management really is. But I think that's in a lot of ways kind of an ideal thing to do. And then between services, you can have Clojure spec or prismatic schema, whatever you want, to define the interface. And that way, everybody knows what the next service will expect. So we've learned kind of the hard way a few times to really treat the database as an implementation detail, and you really just want one or maybe two services talking to a database. You don't want any more than that if you can help it. Otherwise, it becomes really hard to make changes in that database. And when you're growing quickly, the database can often become the bottleneck. Something where Postgres is working great, and then you need to switch to a distributed solution at some point. If there's 5 different services all reading from that database, it's a difficult migration. Whereas if there's, maybe one service that reads and one service that writes, great, no problem. You have a migration path then. So I want to give like an example from the early part of my work at AppsFlyer. This is sort of the stack that we inherited when I joined. The browser would talk directly to a Python Django service, and the Python was lots of code, and scattered throughout that code were database calls all in all different classes throughout the code. At the time, this Toku database was dying on us, right? So queries would take 30 seconds for our large clients. Queries would take a minute. And we're really stuck. You're like, what are we going to do? So, we thought, well, maybe part of the problem is that the Toku, it both has to take a really high rate of writes, all the real-time data coming in, and it has to support reads. So we'll just truncate the history, move that into a historical Toku, and then we'll have a new one that accumulates the new writes, and then when we need to read, we'll read from both of them. and aggregate the data in the client. This sort of helped. Then in front of that, they wrote a pre-aggregation service that would use Redis to pre-aggregate some of the data so especially for the organic data, that's data that doesn't have a attribution media source, or it's not Facebook, it's not Google, it's just somebody installed the app. There's a lot of that data, it doesn't have a lot of dimensions, and so you can aggregate it and reduce the load. So they wrote this aggregation using Redis to hold some keys, and that helped us hold on for a few more months. But eventually, this was totally not working. So what I did was I wrote a Clojure service that would sit on top of the Toku and expose roughly the same API that the Toku was exposing. And so then, and then at the same time, they happened to be rewriting the upstream part of the stack, and so they connected to this API that I was exposing. So once we had that in place, we're still hurting, but it's a lateral move, and now we were totally ready to go. So first thing we did was we had some experience with Druid, and so we replaced the Toku with Druid, and now the API doesn't change for the client, even though Toku and Druid have completely different APIs, different semantics. One's a document store, and the other is a columnar database with really interesting performance. And that worked for a little while. Because of the shape of our data, the Druid was not actually the perfect solution for us, and so we switched now to a Lambda architecture where we had MemSQL taking the live updates and holding data for just 1 or 2 days, and then the rest of the data would be held by Druid. And then every day we would kind of process with a new batch of batch data. And that worked okay, except MemSQL was not super stable in our hands at least. And so currently what we're looking at is a stack where we use ClickHouse to take the live reads, and so we have a Spark service that reads from Kafka and streams the data into the ClickHouse nodes of the ClickHouse, and then the older data is being served by Druid. And all these changes were really only made possible because we had this stable API that we could expose to the clients upstream, and testing is much easier, right? It's not a turn it off and turn it on thing, right? You turn on a new version, and then you can decide to move some of your production traffic to it and see how it does. You can move it back. You have so much more flexibility once you create a stable layer in front of your database. So don't let too many people talk to your database. It's really bad.
You characterize these microservices, they all depend on the data in one database, or they have their own separate databases?
By and large, they have their own separate databases. So let's see, the major databases in the real-time flow are these key value stores. And essentially what they're doing is after we receive a click, they store the click there, and then when we get the install, we can look up the click and see if it matches. So that's one, and so that's largely just a database for the attribution engine. And then between the attribution engine and this activity, there's another database where we store the match that we made. So once we decide you are attributed to Facebook, then we put that in an Aerospike, and that stays there forever. So that's largely a write by the attribution engine and a read by the user activity. And that's largely, like you say, just one, or I say two. Sometimes two is okay, right? If you have one service that's writing and one that's reading, but you definitely don't want to have more than that.
Does the Aerospike require like the key space fit and RAM? And if so, like how do you handle that with the amount of data that you guys are getting?
Right. So one, we have a lot of nodes. I think I can't give a number, but I think at least some of our clusters are at least 100 fairly large Aerospike nodes. And then two, they don't store the UUID for the key as just a string. They store it as bytes, and it's much more compact that way. So that helps a lot. And this is actually one of the big wins with Aerospike, is that the keys are in memory. So for instance, for this user activity, most of our data is organic, so it won't actually have a hit here. So by having the keys in memory, Aerospike can make a very quick check. Yes, it's here, or no, it's here. And then if only for the few % that are non-organic, does it actually go down to the disk and get the data back. So that's a big win with Aerospike as well, that you have this flexibility. Good question. So we run on AWS almost completely. We use Google for BigQuery, but that's basically it. Currently, we run on one availability zone in Europe, but we're now switching to run on multiple availability zones, which is its own talk that I won't get into, but it's a pretty big challenge to take something that runs in one place and then suddenly put hundreds of milliseconds of extra latency between the services. These Clojure services get packaged into Docker containers, and we have our own kind of hand-built deployment system that is able to deploy those Docker containers onto all the nodes. Together with that, we have our own home-built auto-scaling that can scale up and scale down the machines as needed. And we also heavily rely on Spot instances from AWS. So I don't know if everyone's familiar or not, so I'll explain. For roughly 20% of the cost of a normal machine, you can get a machine from AWS. The only catch is that they can take it away whenever they want. So we use these pretty heavily because they're so much cheaper. But what it means is that we need to be able to very quickly shift our deployment. If we get all of certain spots taken away, we need to shift to other instance types. There's a lot of details in terms of the spot management. I'm not sure how current this is, but we have a lot of machines that you can read about. It's an enormous infrastructure. And I think I'll just briefly mention, and I have a section here, but I don't think I really need it given Tiago's talk this morning. So one day our CTO came in and he had a stack of hard copies of Michael Nygaard's Release It. He gave everybody a hard copy of this book, and then we journal clubbed a chapter of it every week for the next month or two. And it just goes through in plain language how to make things stable. So, you want to use queues. Queues are great, right? Because when the consumer has a problem, the problem goes back to the queue. It's not the producer's problem, and that's a huge win. And also, Rich Hickey's talk said queues are great, and he's right. Timeouts, as Tiago said, anytime you reach outside of your machine for something, you should be aware. Even on your own machine, anytime you reach out of your JVM, that's a time that you need to think. What happens if it's not there? Do I care? Maybe I can make it not matter so much, and that's really been important. And circuit breaking is super, super important. So that's it. And I'll be delighted to take more questions now or later. Yeah?
I have one question about the graph you showed very early on. It was more or less like a straight line. What I'm really curious about was if it really was a straight line, or if you experienced more sort of big bursts of growth, and how that affected your choices of technology.
Yeah. I was also, because it's a lot bigger here than what I'm used to looking at, and also surprised that it was so straight. So I know, like, from looking at the revenue of the company, it's not straight, it's exponential. So I think I don't have a great answer for you. So, but along those lines, I'll say that spikes are something we hit a lot. So there's an app in India that every time there's a cricket game, it doubles our traffic. One app, you can think of, the size of that market is incredible. So we start watching the cricket schedule now. Yeah.
You said that you were using Redis, or I guess Redis cluster or something like that. Do you know why it stopped scaling? I thought it was like Kafka, and you were able to scale it like as well as more.
They were using Redis for PubSub. So I think we still use Redis as a general key value store when we don't need like the Aerospike sort of availability and performance. But for the general message queue, we don't use it for that anymore. Yeah.
Could you touch on how you guys are handling testing and coordinating like microservices where they might depend on certain versions and like integration tests, everything? How do you handle it?
Yeah, it's a good question and a hard one. So the question is, how do we test things, especially if it might need a coordinated change, or how do you know if your change affects a bunch of things that you don't even know about in the system? So currently, they've got a pretty good system up now, and it's taken maybe a year to get going, where you can define in a fairly declarative JSON format which services you want to be launched and what environment variables they need to be set and which specific configuration. And so you can get a fairly large part of the stack set up. And currently, I think that runs on a Mesos cluster, launching Dockers on a Mesos cluster, although I believe they plan to transition it over to Kubernetes. But that's working pretty well. You can bring up a whole isolated staging cluster, and within it, it has its own kind of DNS scope. So when you refer to services, if you do it correctly, it'll find the version in your staging environment. So that's working pretty well now. And, but it's a work in progress. It's a great, yeah.
Just to follow up that, you had mentioned that you always try to stay like 10 times. Being able to process 10 times, that's the credit processing. How do you simulate that? That's a lot of events.
Yeah, yeah. Honestly, some of it is not not just, some of it is maybe you're pretty sure you could do 10 times on the current architecture, but you know that it would be cost prohibitive. So you can see that if like you just scale what you have, that it would cost too much. But yeah, to generate 10x, there's some tricks. You can sort of take the data and copy it or loop it, run the same data but at a much higher rate. That's another option. But yeah, it's hard to really, it's really hard to test the load at scale and make sure that you're really, really testing it correctly. So, yeah.
Sorry for all those questions.
No, great.
But it's really fun to see someone with the same problem, right?
Yeah.
I've heard that you said before that you were using Spark for streaming pipeline, right? Have you considered to use Onyx, or did you try to use Onyx?
Yeah, so maybe I'll explain the main reason that we're using Spark is because the code that knows about the transformation from JSON to these known entities in Parquet, that code is written in Spark. And so it turns out we need that same knowledge of which JSON fields map to which known sort of global entities. We need that same code to load ClickHouse, and that's what's holding us back right now from using another implementation, is that our schema is actually locked up in the Scala code, and we don't know how to get it out yet. It's a work in progress, but I wrote a little POC in Onyx though, and I liked it a lot. So to do this exact process to load ClickHouse. So great. I think I may have used up all my time, so feel free to please talk to me afterwards, and thank you, everyone.